Okay. All right. Hello, everyone. Simon reveal at 1 million subs. Yeah, Taylor, exactly. All right. Hey, everyone. So today we have two exciting things. Basically, a description of assignments 1 or 2 and 3. And we'll be covering concepts of transfer learning. So without further ado, I guess as a general disclaimer, as always, these are recorded. It's going to be publicly posted. If you have any issue with that, just let me know. Questions can be thrown into the chat. I'll check it regularly. All the same old spiel. ML Weekly this week is well, it's not as I guess in depth as it's been in previous weeks, but it covers some really interesting stuff. Hard to not include some kind of relation to the ongoing elections, and I mean ongoing as in very much ongoing. I'm pretty sure during this tutorial itself we might get more news. But something that's really interesting, Ottawa-based, AI-related. There's a company called Advanced Symbolics who has this basically NLP social media-powered AI that they call Polyvote. And Polyvote in previous, hang on, let me move this here. In previous elections, so they ran their model through basically social media content from different users in different parts of the states. Just they have some ways of trying to generate predictions or election outcomes, and they did that prior to the U.S. elections. And I mean, just kind of one-to-one comparison, they're pretty spot on. Previously, their polyvote system in the 2016 election actually had predicted a Trump election, and they had also predicted Brexit, the outcome of the Brexit vote. So very interesting because it's both Ottawa-based and kind of like large-scale NLP on social media data. They are a startup, if I understand correctly. I actually interviewed one of, I think the CTO a few years ago for an article I was writing as part of another journal. But anyways, for those who are kind of interested in politics, in NLP, kind of big data, social media, this could be a company, at least here locally, to keep an eye on. So that's kind of from like the NLP field, election related materials. We're touching on transfer learning this week. And so something, if you're not already familiar with this framework, it's very much one I think you guys would enjoy playing around with. So here's using what's called like Tensorflow Js. It's basically an in-browser kind of TensorFlow implementation. So you can kind of generate and build an experiment with models client side. This is basically like a neural network playground where what you can do is define certain kinds of input features. You can change the ratio of training test data, how much noise you want as part of between the different classes, batch sizes, and the likes, and you can kind of like regenerate the data set. You can choose what kind of distribution you want the data set roughly to fall around, and you can then toy around with parameters of the network itself. And then you set a bunch of things like learning rate, your activation layers, whether you want to apply some form of regularization, and then you hit go. And what you can basically, well, it's not so obvious here. Maybe if we discretize the output, yeah, anyways, what you basically see is the decision boundaries kind of being formed live as this model is learning. You can actually see it's all in the direction of trying to really like demonstrate what different layers and different neurons and different parts of the network are doing. You can see there's a lot of, and so like the width of these lines is kind of the weight of each of the features into each, and you can like dynamically just like add more layers if you want, add more neurons, and kind of restart the process. If we say reduce the amount of noise, you can kind of get a general sense for how different parts of the network contribute, or different parameters contribute basically to the predicted outcome. And here is basically like the confidence intervals, or the confidence bounds around. So you can tell like within, I don't know how many epochs this was, but we pretty quickly learned the decision boundaries. And by hovering over these, we can see what each of the neurons is basically contributing to the decision boundaries. So it's like a really, so early in the network, we learn more like linear type features. those in combination. So you can see a lot of them are kind of pushing down to the slower bit really to get this rounded thing. You can see that contributes a lot to these kind of additional 2 into this output layer. Like this neuron here is basically doing nothing. It's kind of like a dead neuron. These ones as well aren't really contributing much. So you can kind of get a general sense for like what's going on under the hood. And by just, I mean, same network parameters, different distribution, how does it do, how doesn't it do? You can add on kind of all these input features, test it out. And like very excitingly, you can also do some kind of more interesting stuff if you want to do kind of like here's a whole bunch of input features and we want to do maybe, whoops, we'll do more of like an encoder, decoder type network. So kind of we bottleneck to this third layer, which will have only 1, and then we'll add another layer, and we'll, so like kind of bottlenecks in is kind of like the encoding and then the decoding, just to get a general sense for how that type of architecture might be good or not, or you can add additional layers or like neurons within each. So this is more of kind of like a ResNet type, so it's just like a deep neural network with roughly the same kind of like shape throughout. Yeah, over like time, you can kind of get a sense for how these things change. Anyways, just like very exciting implementations of like even just in browser neural networks to just start playing with these things. I'd highly recommend everybody kind of take a pass at this, just like play around with these things. And similar to that, more on the vision side, and again, with the idea that we're going to get ultimately to transfer learning near the end of this tutorial, so we can also kind of visualize what different types of layers for different types of networks, what the features within them look like. So this is using Google.net. So that's this one here. The idea is we want to kind of understand what the network sees or what it like it interprets at different parts of the layers. These have been like kind of cast back into the color domain. Most of the time they're not in like 3-channel color, but you can see early in the layer, you learn things like edges. Later on, you learn things that are more like textures. So this is all, again, distill.pub. I had introduced this a few tutorials back. Really amazing stuff in the visualization space. A lot of it actually is based on Chris Ola's vision for the future, a guy actually from Toronto, who's working, well, Google Brain team, but also I think now currently at OpenAI. Anyways, later on in the network, you learn things like pattern, parts. So this could be like dogs, snouts, types of things like flower features. And then later on, like objects. So like arms, hands, legs, what looks like eyes, pieces of buildings, actual dog elements. Anyways, so reading through some of these articles, you get a really good hands-on or like a really good intuition as to what's actually going on at different parts of the layers within a vision-based neural network. So anyways, ML Weekly kind of in a pinch. And so today we're actually going to be covering some of those elements later on, but for now, grand reveal of what the course projects will be. I'll basically be covering what assignments 2 and 3 are going to be. Based on the contents of assignments 2 and 3, I'll cover a brief tutorial, well, brief. It'll be a pretty actually in-depth tutorial on this framework toolkit called DeepPurpose. And then in the last bit, if we have, we'll probably have enough time, but I'll touch on a tutorial on transfer learning. So, grand reveal, like drum roll, please. The course project will be on actually applying deep learning to predict COVID-19 antiviral drugs. So I'll go over the general instructions. I'm sorry that this is 6 pages long, but I did want to give you guys as much information as possible. And if you guys have any questions, please at any point during as I break this down, if anything's unclear, just let me know. But basically, either individually or with a partner, the premise is you're a lead machine learning research among an interdisciplinary team of scientists and virologists during this very real COVID-19 pandemic. Your team has decided to dedicate their time and resources to identifying candidate antiviral drugs that may reduce the severity of COVID-19 and hopefully the virus's mortality rate. But as is the reality for most research labs, your team only has the resources for a handful of candidate antiviral drugs among the millions that exist. So they turn to you and your team of machine learning engineers and data scientists to generate basically a deep learning model that can predict which of the millions of drugs is most likely to cure COVID-19. From that list, you can provide them with a short list of the candidate drugs that they would then take into the lab to actually validate using wet lab techniques. And hopefully if it works, then you can help cure COVID-19. So time is ticking, lives are at stake. Can you bring an end to the pandemic? Da, 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 da. Anyways, so assignment 2 and 3 are basically developing machine learning models for what's known as drug target interaction prediction. So like I said, they can be done independently or in teams of 2. Assignment 2 has really 2 deliverables. There's a notebook with a number of different questions that are really targeted to getting you guys familiarized with the DeepPurpose framework. So DeepPurpose is basically this like API toolkit that really actually makes easy or like really facilitates converting a lot of these protein drugs and protein sequences into something that you can easily port into a machine learning framework. So basically, if you get a good handle on how this works, you'll be able to complete assignment, well, 3 hopefully with relative ease. And the second deliverable for assignment 2 is a written proposal. So assignment 2 is really kind of like getting you familiarized with the framework and getting you thinking about how you're going to use it to come up with basically what the last implementation or your final machine learning solution will be as part of assignment 3. So basically what you write up and propose as your machine learning solution in this proposal, it doesn't necessarily have to be what is actually implemented, but it should be pretty close. So the deep learning or the DeepPurpose framework makes it easily accessible to basically feature represent protein sequences and drug sequences. And as I say, in assignment 3, you're going to develop that model, and then we're actually going to have your model compete against others in the scientific literature. So like other existing methods that are already out there and published, as well as against the models developed by your peers. So like each of your models will be competed against one another and also benchmarked against others that exist. If you guys can beat the state of the art out there, and if we can actually create maybe from your models an ensemble classifier as part of what I think is a pretty decent or perhaps a reach goal, would be to combine your models into an ensemble predictor, use them to generate predictions for this data set of about 50,000 drugs that are candidates for COVID-19. And perhaps if this actually does perform pretty well and we actually get some interesting results, I'm hoping to perhaps try and wrap this up as an academic research paper. So kind of an exciting reach project or reach element if we can make it happen, but if not, well, it'll just be a fun competition amongst us. So I'll just like go over some of the backgrounds and just give you guys maybe perhaps a better sense as to what drug targeting interaction really is. So it's basically trying to figure out figuring out which drugs will cure certain diseases is super expensive. Trying to come up with a new compound is usually, like in the wet lab through experimentation, usually takes about 10 years and is on the order of about $2.6 billion. So one strategy to figure out whether one given drug will target a certain disease is to figure out if an existing drug that's out there can be useful. So that's something that's called drug repurposing. But there are like millions, billions of candidate drugs out there. So figuring out which one will work for a given disease is, again, very expensive to do in the lab. So there's a lot of interest now to use computational techniques. So very recently, there's a lot of deep learning models that have come out for drug target interaction prediction. So I guess before I touch onto this, so the way that you can think about drug targeting, so target proteins. So in say the coronavirus, you've probably heard a lot about the spike protein and people trying to develop drugs that will kind of disrupt it. So basically the idea is you have this kind of like protein that's out there that has to bind to human cells and infect the body. The idea is to have a small molecular drug come in and bind to it very strongly and hopefully disrupt that process. So if you can prevent it from binding to human cells, you can effectively prevent the virus from kind of entering and taking over the cellular mechanism. So it's this idea of like a lock and key. We want to basically find the right key, the drug that will basically fit and bind to the right part of that protein. And so how strong or how well it binds to a protein is something that's called binding affinity. So you don't have, again, you don't have to know all the biological stuff behind this, but just to get like a conceptual overview, the binding affinity is just, again, how strong the drug will bind to the protein. So it's the equilibrium dissociation constant. So here the word is dissociation. So if the dissociation, which means like, disconnection, if that's very low, then it means it binds very, very strongly. So a very low value, KD, kind of this score that we're going to want to regress on. If we can predict for a drug and a certain target that score is extremely low, then that has that's a very good candidate to look at. However, it's really high, so the likelihood of it disassociating from the protein is very high, then it's not a very good candidate. So all things said, so I guess really here, for the purposes of this assignment, you can just think of the dissociation constant as the float value we're going to try and predict, which is good for regression type models. And so how do we actually encode these things? So this is very different from like images, but we can think of this almost as maybe more of like an NLP like task. So both proteins and drugs can be represented as sequences, and they come from kind of two different alphabets. So just a bit of notation. So proteins are represented as a sequence of amino acids, whereas molecules can actually be represented as what are known as simplified molecular input entry line system, so on and so forth. You can just call them SMILES. So a protein SMILE, I'll just like zoom in, is something that looks kind of like this. So for a given drug, there's a certain like process by which you can encode all the atomic elements of this into basically a sequence of characters. So this basically turns into this sequence of N1, CN, so on and so forth. So this is basically a sequence that will represent this molecule. And similarly for proteins, I'm sure you have a general idea that proteins are just chains of what are known as amino acids that kind of connect together and form these like 3D structures. And so they come from this alphabet of 20 amino acids. So things like M, A, L. So you can kind of think of these as like sentences or words from which, you would learn things about the English language. But here we're going to treat these sequences and, well, protein sequences, amino acids, and SMILES as just kind of the two input things. If we can turn these into numerical vectors, we can then just feed that into our model and then do a bunch of deep learning on them. So that's something kind of like this. So again, a given drug, pseudoephedrine is basically this sequence of characters. The alpha-2A receptor is an amino acid sequence that looks something like this. And we can then put it into a framework that looks kind of something like this. For a given drug, we encode it into a vector for a given, through like some sequence 2vec or some other, basically encoding process. And then similarly for a amino acid sequence, we'll call these targets. So the drug will try to bind to a target. We encode it in a certain way. We can concatenate these vectors together and then just feed this into whatever neural network that you want. So the DeepPurpose library that we're going to look at will actually make pretty easy this whole like pre-processing step. And then when you concatenate or like feed these into whatever model, really in assignment 3, you guys will be developing kind of this later stage learning thing. Basically, you'll be you'll feed in these vectors into your model and generate basically a binding score. And just, I guess, like a foreshadowing note, you don't need to restrict yourself to only one type of encoding. So there's many, many different ways that you can kind of encode a drug or a target that capture kind of different features about it. And you can kind of, grow this input vector into kind of whatever dimension or shape that you want. So just something to keep in mind. Later on, I kind of touch on a few different models or like methods that have incorporated stuff like this before, deep DTA, different like graph neural network implementation, some deep convolutional neural networks, so on and so forth, really more for the point of just getting you guys familiarized with some of these methods that are out there. And what's really promising is basically if we can come up with a really good architecture, a really good representation, and a really good model, we'd be able to then develop a robust model to like screen all these candidate drugs to basically see whether any of them can interact with a very low KD score against the coronavirus protein. So just again, from nomenclature, the coronavirus that currently exists or that's currently afflicting the world and that causes COVID-19 is SARS-CoV-2. to be distinguished from SARS-CoV, which is the original one from 2002, 2003. Just like a point of to clarify. So briefly, so yeah, the idea here is basically to use the DeepPurpose toolkit. So what's really exciting is, so Kexin Huang from Harvard University developed this entire framework, and it's basically a scikit-learn-like framework. So it wraps up a lot of these different models, implementations and everything into what is basically like 10 lines of code. So it abstracts away a lot of the work. It makes very easy loading and having access to a lot of these data sets that we would use for these types of things. And he has a really great like overview blog post towards data science tutorial. I'd recommend everyone kind of go through that. And what's actually really exciting, even posted on his GitHub page, the features that he has like quoted is like 15 plus powerful encodings for drugs and proteins, ranging from deep neural networks on classical cheminformatics fingerprints, to CNNs, to transformers, to message passing graph neural networks, with like 50 plus combined models. And like the exciting bit is that most of the combinations of the encodings do not exist yet in like scientific literature. Like people haven't tested these things out or like compared them. And these are all easily creatable under 10 lines of code with lots of flexibility. So actually switching between encoding is as simple as changing encoding names. So that's kind of the exciting bit here is with a whole bunch of people in this class, if you guys are all interested in different kinds of like playing with different kinds of encodings and embeddings and testing out different things, it will be interesting to kind of explore that space and hopefully come up with some really exciting models. So I then touch on to stuff. This data and experimental design is just kind of like a rough overview of kind of the benchmark data sets that are out there. Really, there's like this Davis, Binding DB, some information about them. Mentions things on like whether you might want to balance or not balance your data set. The concept of cold target. So the idea is that in your test data set, you might want to ensure that none of the proteins and none of the drugs that are in the test set appear at all in the training and validation sets. So that's like for the point of model generalization or generalizability. If you're coming up with this brand new virus with brand new proteins, it's a good way to measure how well your model will actually perform on completely unseen protein sequences and potentially completely unseen drugs. So that's the concept of kind of like cold target or cold drug. Briefly touches on how things could be split for training validation test sets and different metrics you might consider. And just as a point, if the KD, so if your binding dissociation constant is less than 30 by convention, if we wanted to turn this instead of a regression problem into a classification problem, that is typically the threshold that we'll use. So anything with a dissociation constant between a drug and a target that's less than 30, we would call a 1, a positive. So they would in fact bind, and anything with a KD that's greater would be called a negative. So anyways, just to point out. So these are basically the deliverables. So there's two. So creating a model with the DeepPurpose framework. I outline a bunch of these different steps, but instead of going over them here, you can refer to them in into the template notebook. So there's a notebook that kind of gives you all these different steps and all the kind of like placeholder code that basically wherever there's like a to-do, just like fill in your solution there. And then the last part is the written project proposal. So this is where after you've kind of played around with DeepPurpose a little, gotten a good idea as to how it works, and maybe familiarized yourselves with some of the types of encodings and the way these things are represented, basically propose what you plan on doing and what you yourself and you with perhaps your partner will do as part of assignment 3 as your kind of like finalized project solution. So the idea here is to kind of model this in such a way that your audience would be like your interdisciplinary team of scientists and other machine learning engineers. So think of this as like a scientific proposal of the work that you plan on doing that you would perhaps present to them. So you would want to cover a number of different things. You want to have a brief abstract. You'd want to give them like a project overview. So I kind of break down things you can talk about. You're not necessarily held to these things. These are kind of like rough guidelines. But you would talk about, what is drug target interaction? how can drug target interaction predictors be leveraged for COVID-19, describe a few, so kind of like a mini lit review, describe other methods you've perhaps looked at and maybe want to model your solution after. Your proposed data and methods, so what kind of data sets do you plan on using? How do you plan on transforming and representing? So from the DeepPurpose, we plan on leveraging these kinds of representations, perhaps briefly describing what those might be. Talk about the architecture, so how from those representations you'll feed this into your network, and any of the experiments you'll do to kind of optimize that and improve the model. Strategies to promote model generalization. I'd strongly recommend everyone include kind of a conceptual overview figure as to kind of each step of that pipeline end to end. And then maybe just briefly touch on what you expect your results to be, perhaps based on preliminary work that you, or experiments you've already tried out, or otherwise. So this is just to get you guys really focused and thinking about what it is that you'll actually do for assignment 3. And I know a lot of people tend to favor Word, but most of machine learning in the field operates in LaTeX. And if you haven't already realized, all the documents that I've created here are all done in LaTeX. And so as part of the requirements and to get you guys familiarized with what formatting a LaTeX document looks like, basically you'd have to submit a PDF format of your proposal that follows the IEEE conference style. So I strongly recommend you guys use Overleaf. So just as like an example, if you haven't already used it at all, this is Overleaf. This is the IEEE conference template. So it's basically a 2-column place. You'd put your basically just like a brief title as to what your method is. I don't know, give it a fancy name or something exciting, like Deep DTA, or I don't know, whatever. I know Chris, you can call it like ChrisNet or something. I know, come up with something fun. But yeah, you basically fill out your proposal as part of these things. Is LaTeX easy to use? I was asked by Jay. That will be for you to figure out. It is definitely, it's like a markup type language, similar to Markdown or like HTML. So it's all about using tags. But I think something that's pretty important is if working in the kind of machine learning space, it's pretty important to work on this. It's not so bad, definitely different from what you see is what you get. Yeah, exactly. I mean, just as an example here, let me just briefly touch on this. You click on, if you create an account, you click on that button, it's basically this. There's a lot of kind of like extra fodder stuff that you don't want to touch. But what you can do is you go into places here where there's like these author tags as part of an author block. You'll put in your name and whatnot. And then like down here, there's like sections, subsections. You basically fill in material. If you want to have references, so you can put references into like a BibTeX file. For those who don't really know too much, there's a lot of good like online tutorials and stuff, but or you can keep to like very like simple formats. I might also create a template that maybe differs from the IEEE one. I only choose IEEE because this is kind of the typical 2-column format for most like scientific articles and stuff, or like technical documents. But yeah, we'll like touch on this, but basically just get a good sense for how these documents come together. I'd strongly recommend don't leave this to the last minute. Toy around with LaTeX. And also just as a point, it's a compiled language, or like it's a compiled document. So let's say for the title, I want to say paper title, I don't know, I'll call this KevinNet. And I would recompile this and it will update the document here in this PDF reader accordingly. So yeah, anyways, play around with this. This is kind of the general format that will need to be followed. Oh, I guess I lost my, let me go back. Yeah, here. So all that to say, that's kind of the second deliverable, and all again in anticipation of assignment 3. And I list a bunch of project resources here. So there's excellent documentation to DeepPurpose. So there's both like a tutorial to get you started. We'll actually cover some of that tutorial material now pretty quickly since we're already kind of halfway through. I would refer you to the GitHub repo, the documentation. So I'll be setting everything up in Google Colab, but it's definitely not as easy to set up in Google Colab as other frameworks. It's not as easy as like a pip install type of thing. So if you want to run things locally, if you have a GPU, that's a good idea. But I did prepare everything so that you can run it on Colab, but it's a bit finicky. But if you want, you can also set up DeepPurpose locally. Anyways, a number of other things here and a number of other references. So I'll let you guys kind of read through all this, and then we'll basically just jump into the notebooks now. So I guess just like touching up, yeah, I'll cover the DeepPurpose tutorial pretty quickly, just to give you guys like a high level overview, and it's again really well documented, so you guys can follow along. But then I also do want to briefly touch on transfer learning before the end. Let me, okay, this reconnected. So let's do this. So I'll reconnect this. Something that's really important is you want to ensure that your runtime is GPU enabled. And there's all this precursor stuff. So like I say, getting DeepLab or DeepPurpose set up is like to use it is pretty straightforward, but it's not set up right now for like easy pip installation and these types of things. So there is a bit of a setup process here that's kind of hidden away in these steps. So at the start, you can kind of just like click this run button, and it'll take about like 3 to 5 minutes just to kind of like get everything set up for you. But there is one step that requires user input near the end. So if I like start running this, it'll run through, but this will keep running to infinity if you don't actually go in and put that like yes confirmation. So these are things like just setting up the Python paths on the Google Colab end. For those of you using Anaconda, so it's basically like an Anaconda setup. So all these lines is just getting Anaconda set up on Google Colab, which is not usually the way that you do it, but DeepPurpose is actually currently still being developed. So just as this is running, I mean, there are things that are still being kind of set up and worked on dynamically. It was kind of put together last month, and like there are things that are still ongoing. So like even last month, they started to put up instructions on how it can be installed on Colab. But basically, this is kind of like state of the art stuff. Like people, I think, will be using this pretty regularly. So it's kind of nice to have a first pass at some of this stuff. And it's very well documented. So here, a framework for drug target interaction prediction with less than 10 lines of code gives you a very kind of easy breakdown. You kind of load up from DeepPurpose different models, the utils, the data sets. It gives you a sense as to how you can kind of set up and process different things. So you want your X features for a drug, your X features for a target, and a Y value. So if you want to load and set up the binding DB data set, it's literally like this line with a number of different parameters. So as your Y, you want the KD value. We don't want it in binary, say, for example. So for more of a ideas of due dates, I think this is assignment 2 is 2 weeks, and then after that it will be assignment 3 another 2 weeks. Basically, so that everything is due within a month. By December 6th, I think, is the deadline for the final project. So 2 weeks to kind of get familiar with this, finish those questions, write up your proposal, and then after that, just implement it and test things out. But yeah, back to this. So basically, this is like the feature extraction step, or the dataset loading step. When you want to choose an encoder, this is a message passing neural network. So message passing neural network will be my drug encoding. I want to use the transformer based encoding for my targets. There's ways to easily basically encode each onto your data set and then split according to different methods. Again, the concept of like cold protein will mean that test samples, test drugs and targets, test proteins and smiles won't appear in your validation training set. So good for model generalization, a certain fraction by which you want to set up that split. You can configure different models. So here it's basically like a transformer based model with a number of layers. You initialize it, you can train it by passing it these data sets, and yeah, you can also load pre-trained models and so on and so forth. What is Frac used for? So Frac is just the fraction, so the proportion of samples. So 70% goes to training, 10% goes to validation, and 20% to test is basically the breakdown. And then at the very end, you can basically like supply other smiles and other sequences and basically evaluate or test them. So this is generally the framework that we'll roughly follow, but you might want to incorporate, of course, like other steps and other types of things. And there's a bunch of other really exciting things. So there are antiviral drugs repurposing for the coronavirus materials here. Like there's this like one-liner call where you can like repurpose for all the loaded coronavirus, or for this is one coronavirus drug, load all the antiviral drugs, and it does this like repurposing step, right? So it's actually predicting for certain drugs the likelihood that they bind to these things. And so here, these binding scores are actually really high. So you would say that, you know, none of these is kind of below 30. So none of these really would be candidates. Anyways, and so the idea, and it goes into other things. So there's a bunch of these tutorials. There's dataset tutorials, how you might do drug repurposing, how you reproduce deep DTA. So kind of like foreshadowing to what the evaluation, I'll probably be comparing your methods to a method like deep DTA. So if you're interested in trying to recreate that work, there's all these notebooks that are kind of available to doing that. So like I say, very well documented end to end to do a number of different things. I'm just going to jump back here. So as part of the, again, loading and getting set up framework, okay, so we're here in activating. So it's when we get to here, this RD kit, this line we have to input like a yes command. But basically all this does is it sets everything up. So we get to the point where so the sanity check here is as long as these modules, when you run this cell, if there's no errors that show up, you are good to go. And I'll just kind of foreshadow some of the stuff from this tutorial, just because, again, for the sake of time, like I say, this takes about 5-ish minutes to run through. All that we do here is kind of like showcase some of these things similar to some of the other notebooks. I'll leave the reading of this stuff to you guys, but it roughly covers the same idea that why we want to use drug target interaction prediction, how we can load the data, drug smiles as strings, and protein sequences as strings. So here's just like as an example. So you can also read in from files. So if you want to upload your own file to experiment with, it tells you the way to do that. So here's just like a command to read these things in. You can print out a number of them. So here it just shows what the smiles value are, what the protein sequences are, and then the value. So again, this smile, this sequence-based representation, we're going to want to encode some way. This protein sequence will want to encode some way. You can load existing data sets, so load and process the Davis data set. Some of these things aren't required. So again, just like refer to the data set. The convert to log is actually converting the regression scores, the KD scores, onto a log-based distribution, as opposed to not, that you can like experiment as to whether or not that's good or bad. Typically, a log conversion makes the regression task a bit easier. So another parameter to play with, again, threshold by default is set to 30, but you can specify as well if you want it in binary. So if binary was true and threshold was say 10, anything with a KD less than 10, such as this one, would be a 1 instead of 7.36, so on and so forth. So 1 or 0 as a classification task. All that to say, so then if you want to encode something, you can specify what kind of encoding you want to use. So this is, again, message passing neural network for the drug, a CNN-based encoding for the target. We could split that up into certain types of, into certain ways. It will then spit out basically, so say for the train data set, it'll be a data frame where we have smiles as a sequence in one column, target sequence, so the protein amino acid sequence is another, the label is your KD value, and then here you basically have throughout this entire data frame all your encoding. So this doesn't actually like list them out, but these are basically tensors. So they're just the outputs of the message passing neural network applied to this. So what you'll want to feed into your neural network, say as the smile encoding, is basically this object here, and then similarly the CNN-based encoding for the target would be in this column here. And I guess going back to let me just find it again. So DeepPurpose. So if you want a list of all the possible encodings that you have, again, on the GitHub page, They're all here. So it's like, here are the drug encodings. You can use Morgan, PubChem, Daylight. These all mean different things. And this is kind of up to you guys to kind of figure out which you guys think might be better or worse if you experiment with some of these. How would a neural network we build handle variable length inputs? So actually that's taken care of at the, since not all smile strings are the same. So yeah, that's actually taken care of at the encoding phase. So the outputs of most encodings will be the same shape. So you don't need to worry about that so much. And so some of the types of encodings will limit the amount of information, or the length will be, will be limited to, say, the first 124 or 1024 characters or 512 characters, but be careful as well. These will all generate different types of shapes of inputs. So what you get from a transformer-based model might differ from the daylight representation, and from say like the pseudo AAC, pseudo amino acid composition. So again, these are for targets. So these are for protein sequences. These might all end up as different shapes, and that's kind of up to you to just like experiment with, play around with. Some might be easier than others. So yeah, just really kind of like toy around with some of these things. And you can also, from a transfer learning standpoint. So let me actually let's go here. So under, say, the demos. So this is a beautiful data set, or well, set of notebooks that you can kind of refer to. So if you want a message passing neural network for the drug encoding, and this is like an amino acid composition for the protein encoding applied to the Davis data set, well, here's a demonstration of that. So in like basically, again, a couple of lines of code, this will leverage kind of existing networks that are out there. But really the assignment 3 will require that you kind of actually build out your own like Keras-based network. But this is a good way to kind of get started. So for example, generate a configuration according to these parameters, and you initialize your model with it, and then you train it. And so this is using CPU. So now that, so if you have this all set up on GPUs, and I strongly recommend you use GPUs, because some of these things could actually take, even on GPU, if you do like 100 epochs, it could take a couple of hours to run. So either limit by epoch, but then you don't get as much training. Like even here, so if you look at loss as an example, you can cut off, your training past a certain like iteration, after the first 1,000 iterations. So after a certain number of epochs, it's kind of already a learned model. How do we use GPU or set it is one of the other questions. So again, I'll do it here. So I'm going to start bridging over just into the transfer learning notebook, just to make sure we have enough time to cover it. If you have questions about the assignments, feel free to email me and/or Jim about it, and we'll hopefully like clarify a lot of these questions. But so for the question of how do you set in a notebook the GPU, you'd go under runtime, and then change runtime type, and then here you can choose none, will be CPU only. GPU will be some GPU device, and then a TPU is a tensor processing unit. I haven't toyed around too much with TPUs, but yeah, basically you would set GPU, you would save that, and just be careful if you run through the DeepPurpose setup steps, and you haven't set the GPU as your runtime, you'll have to restart your runtime with the GPU, and then you'll have to again go through the those steps. But basically, once you've initialized this, you can see your RAM, how much RAM you're using, how much disk you're using. And so for the sake of kind of just making sure we actually cover transfer learning concepts in this talk, I'm gonna transition to here. And again, if you have any questions about A1, A2, read the instructions, refer yourselves to the template notebook and the demo of the DeepPurpose framework. And now I'm just gonna like quickly transition to here. So I think you guys covered transfer learning relatively recently. And the intuition or general premise behind why you would want to do transfer learning is because deep learning networks are very, very expensive to train and to develop on mass, like at large scales. So they usually typically require both a massive amount of raw data, such as images, as well as typically high dimensional data. And to optimize millions of parameters, there's like thousands or millions of parameters. You also have to do millions of vectorized computation. So like things like matrix multiplication. And just as a note, that's why GPUs tend to provide so much speed up, is because if you can perform these matrix multiplications on a GPU as opposed to a CPU, you get significant speed up. So that's why you definitely want to make sure GPUs are enabled for these tasks. And so the idea really is we have a huge amount of data, and we develop a really great network for a very specific task, and we spend a lot of computational resources doing that. And so we can afford to train that great model, but then why can't we reuse that model for another or like an analogous kind of task? So we've invested all this compute power into training and optimizing these kind of feature representation or feature learning parts of the model. Just again, as a reminder, we learn things like edges and stuff early in the model. We learn then textures, we then learn patterns, then we learn parts. But as we go deeper and deeper into the network, it's only when we get near the end that kind of assembling all these pieces together is really used as part of the classification process, or like the regression process, right? It's when you actually spit out the object. So for many tasks, actually, the early parts of the network should more or less be the same. Really, all you have to do is kind of adapt those final layers for the specific task you have in mind. So so that looks kind of something like this. Instead of having a large data set for learning this very specific task, and then another large data set for this other specific learning task, why not use that original large data set, learn the system, and then just kind of adapt the end of that pipeline, or adapt it to then develop a new learning system that's kind of at the kind of early stages, or at the early layers of that network are basically the same as the original task. But what we've done is we've kind of like transferred those like feature learning steps and applied it to this other task. And what that has as a consequence is we only need actually a very small amount of data to then kind of fine tune or relearn or optimize those last steps of the model. So this is kind of the concept of what transfer learning tries to get at. And so you guys are free to read all this stuff, but in essence, this is the strategy. You would load the weights of a pre-trained, already optimized deep learning model. You would remove the last few output layers. So just get rid of the things that was required by those specific, that specific task. Then you'll attach new layers on, suitable for whatever task it is that you actually care about. You'll then freeze all the weights, all those original weights of that pre-trained optimized model. You'll then train the new data set. So the only learnable parameters in this network, because we've frozen or like held fixed all the feature representation layers of that optimized deep learning model, when we do this new training step, the only optimized parameters will be those at the very end, at the output layer. So we have those learned for the new task. And so what we've effectively done is transferred, we've performed transfer learning for this like new optimized model, kind of like a hybrid of that original one, but with the new task at hand. So again, to just like quickly demonstrate what this would look like, we're going to use the CAIFAR dataset, and the general strategy is we're going to stack on top of like the feature extraction layers. We're just going to have a classification layer. So because I can't train or like demonstrate the training of a massive neural network on one GPU on Google Colab, we're going to kind of like simulate what this looks like. So what we're going to do is, so CAIFAR is called CAIFAR 10 because there's 10 classes. So what we're going to do is just split up CAIFAR 10 into kind of two different tasks. The first data set will have 5 categories. We'll call them just the classes 1, 2, 3, and 4. So that's like one set of images for those classes. We're going to learn, like train a model on it. We're then going to freeze the feature layers of that model. We're then, as we said, stack a new fresh layer, like fully connected layer on top. And then we're going to see if we can learn a new network to predict the other classes. So 5, 6, 7, 8, and 9. So we'll have taken advantage of the features learned on the kind of first task, on the first set of the CAIFAR data set, and then see if we can do well on the second one. So what that roughly looks like, this is again just importing a bunch of different stuff. This is just like setting a few feature or like parameters that we're going to use throughout. So this is where we kind of set things up. So we'll download from the University of Toronto the Chi-Far data set. And we're going to basically just, again, as always, split this into a training features, training labels, testing features, testing labels, and just like reshape them. As a reminder, there's 50,000 total samples within here, within the training set, and 10,000 in the last. And again, we're going to train a model from scratch on the first 5 class. We'll call those the less than 5 data set. We'll freeze the layers of the model. We'll append a new untrained classification layer to the end, and then train those new layers using the second data set, so the greater than 5. So that's what kind of is going on here. We're just, whoops. Oh, did I forget? Sorry, I forgot to reshape this. So this is just basically extracting into the less than 5 and then the greater than 5 data sets where we're just like splitting this up. As a reminder, these are what the classes are in order 0 through 9, airplane, automobile, bird, cat, deer. So that's our like first data set. And then dog, frog, horse, ship, truck is our second data set. And just to like demo or like show off some of them, you can like run this a number of different times. It's just gonna like randomly pick a few. So these are the categories in our first data set. We'll call task 1. The second data set we'll call task 2. So these are just like sample 32 by 32 images that are colored, so 3 channel. And then we're just going to set things up to actually train the model. So we're doing 5 class classification. The input shape, again, these are 32 by 32 pixel images of 3 channel for the 3 colors, RGB. And then we set up just a few different things. So the feature layers is going to have a convolutional 2D layer. We're going to use ReLU activation. We'll go through another 2D layer. We'll then do another activation. We'll max pool. We'll apply a bit of dropout, flatten everything up, and that will be what we call our feature layers. That's the thing that we're going to use the first model to learn. But the first model will also have to learn a classification layer. So just like a dense layer with activation, a bit of dropout, and then we go into basically our softmax prediction layer. So that's what we'll call our classification layers. So model 1 is literally, we create this as a sequential model. We're just going to concatenate first the feature layers and then tack on the classification layers. And then this is just a, like the training, we'll take in the model, we'll take in the training set, the test set, and the number of classes, and it'll just like kind of run through. It has a timer inside, so it also will show how quickly we can train some of these models. Like we want to compare the performance or the time it takes to train from scratch a model versus transfer learning. So we're going to compare those, and yeah, basically the performance at the end as well. So let's again some more parameters for training. So if we run this, you'll see this is the end-to-end, so from scratch. So again, this is the what we're passing in is the less than 5 data set with the less than 5 labels for training and testing, and then the number of classes. And you can see for each epoch, we'll do this, I think we do this for 20 epochs. You can tell it takes about like two seconds per. So again, this is a simulated example just so that we can kind of demo it in the time of a tutorial. But you can imagine this first step as being something like Google uses 20,000 GPUs to train, you know, Inception v3 on ImageNet, which is like millions of images over thousands of classes, and generates a model with like several hundreds of millions of parameters, right? We're I think only using about 1 million parameters. But then Inception v3 as a model would be the one that you would want to use for your specific task. So you don't want to perhaps classify if a given image is a horse, but you might want to maybe distinguish between, well, part of the assignments from last year was that like from a given image trying to predict which of the buildings of Carlton a given image was represented as, right? So it's like if you have a data set of images of Carlton buildings, can you from that image predict, you know, and maybe like if there's 16 buildings, which of the 16 buildings that might be? So you'll do that as kind of the transfer learning process. So just to demo, this took 53 seconds. Our test accuracy was about 80%, 78%. And then, so yeah, about 54 seconds. And then as a model summary, the thing to note here, so this is basically a breakdown of the network we learned. There's like 1.6 million parameters. All 1.6 are trainable, and the non-trainable parameters here, this indicates that none are frozen. So every single one was learned. So what you can see here is as part of the two convolutional 2D layers. There was like 1700 or 1800 within here. There's about 3700 within here. And then this is like the fully connected layer just before kind of the softmax layers. This is basically the classification output layers. So what we'll want to do in the next part is actually freeze these. We'll want to use what we learned in this given model in these feature learning steps, but we'll still have to learn these other ones. Again, in a very deep and large neural network, these values would be much, much higher, but this is, again, is just like for demonstration. So we can plot the accuracy over time. If you do this repeatedly, this will change slightly, but we can see we generally do pretty well. I mean, we kind of converge around 78, between 78 and 80. And so here, this is kind of like the key bit. So what we want to do now as part of our transfer learning is freeze the previous layers of our model. So there's an attribute called trainable, and if for all the layers in feature layers, if you set that to false, you effectively freeze them. So all we have to do is that, and then so our second model is basically those frozen and learned parameters, but then with a new classification layer on top, or a new trainable classification layer on top. So our second model is everything we've learned from the previous model, but we want to keep these modifiable or trainable for the new task. And remember, the new task has a complete set of 5 classes of images that differ completely from what the first one was. So it's like a completely different task. Still 5 classes, but different objects and different different objects within them. So we set this up just to point out. So the model summary, again, exact same model, except the number of non-trainable parameters is now 38,720, which is just the sum of these two. We still have to learn quite a few in this dense layer, like, so there still is like 1.6 million, but you'll see just how much quicker it is without having to, even though this is a relatively small number, and this is a very simulated example, you'll see just how much quicker this is. So we run this, and now instead of it being basically like 2 seconds per step or whatever it was previously, where you can tell this is already quite a bit faster. The summary is a bit better, but the idea is not having to learn from scratch, not having to relearn those computations is quite a bit. So use the same parameters but different inputs and targets, more or less. So the model is the same model. We're using the same height or model parameters that are learned as part of these layers, but we're now optimizing these ones. So it is a different input and different target, but those are used to tune or like learn these later, these like classification parameters. I hope that clarifies things. But anyways, I hope this is kind of immediately obvious. That took about half the time, even though it was only like 38 million or 38,000 parameters. That took half the time. And our test accuracy is actually quite a bit, like we just got a gain in about like 8% here. So again, we can kind of see, rather than be around between like 78, previously we had plateaued around here. Transfer learning got us up to about 87, 80, 86 percent on our test accuracy. I know we're kind of running out of time here, but I just want to demo. So like when you compare the time it took between each task, transfer learning was much quicker. So here you want to be smaller, about a five-fold, or about half, or about twice as fast. Anyways, so this is just like fold difference. So yeah, in summary, we kind of like touch on these last like few bits. There's always the same takeaway messages as before. We're kind of running out of time, but if anyone has any kind of like last minute questions, I'd encourage you guys all to kind of like play around with this as always. Does anyone have any last minute outstanding questions, either about assignment 2 or assignment 3 or any of the transfer learning stuff? Because if not, I'll give you guys about 30 seconds to type out, because if not, we're a bit over time, and you can always email me. I'm gonna stop sharing. If no other questions, the main difference between assignment 2 and 3. So assignment 2 and 3, so assignment 2 is just a few questions. There's a notebook. Go see in the assignment 2 folder. There's a few questions just to fill out, and it's just to get you familiarized with elements of the DeepPurpose framework. That will help get you thinking about how you want to implement a solution. So it's not actually building out the model. So it just gets you familiarized with the framework. You write up what you plan to do for assignment 3, the actual building, what data you're going to use, what in encoding or like representation you're going to use, how you're going to build your network architecture, kind of plan it out. And then assignment 3 really is just that as a deliverable. You're going to develop it. You're going to report on your performance metrics that you have. One submission per group. Yeah, if you guys pair off, it's one submission per group. If you do it individually, I mean, it's yeah, just make sure you submit. It'll be the notebook and the PDF for the IEEE styled write-up. And as always, so if there are any other questions, feel free to email me or Jim if there's confusion about anything. I can always jump into perhaps one of the course lectures just to clarify anything. But yeah, if there's any modifications or anything, there'll be like a note or something put up onto this, either CU Learn or an email sent around. Cool. I'm going to stop the recording.